Okay, hi everybody. This is the Physics of Bitcoin show with Giovanni and Stephen. It's 4:30, 2025, and I will give you a small introduction, like always, about the show. Basically, it's a show that is focused on trying to understand Bitcoin scientifically using different tools from math and physics, computer science, and both me and Stephen have PhD in physics. We have a kind of eclectic backgrounds where one of the things that it's common between us is that we work in different fields. Myself, for example, in neuroscience, now in analyzing Bitcoin, astrophysics. We both started with astrophysics. We have a PhD in astrophysics, but then Stephen went to work in different areas of computation. Also cryptography. Did you do some cryptography, Stephen? Oh, we lost your audio. Stephen.
How's that?
Perfect.
Okay. We've been doing consulting with OrionX.net, based in Silicon Valley for technology industry for a decade. Yeah.
And what is the focus of that particular?
Really, the focus is on strategy and marketing for high-tech companies, and it can be startups and it can be large companies. So we've worked with all sizes.
And our common experience with using the way that a physicist think and some of the tools that we have developed as physicists are useful to understand several fields. And so we started to also be interested in Bitcoin, both of us at different times, but very, very similar times. And we kind of rediscovered more or less the power law in Bitcoin. We noticed very strong regularities that they are similar to some of the systems that we studied and we are familiar as a physicist, in particular this idea of power laws that are very ubiquitous in physics, like both I and Stephen have pointed out how many physics laws are actually power laws, but they show up also in cities, for example, the economies of how cities grow, many different parameters associated with physics, many different social systems, networks, and so on. And so, we think it's appropriate to use these tools to understand Bitcoin, and we discuss different aspects. We go deeper, and sometimes these discussions can be technical. And so, my suggestion is don't worry about following all the technical details, but if you ever want to go deeper in understanding Bitcoin, you can look at these videos a few times, and try maybe to follow. I think maybe we should always add, and I will try to do that also for past episodes, some links to papers and some references, so you can actually go deeper if you want. It's mostly, it of course is open to anybody who want to hear us, but it's more about, let's go a little bit deeper in trying to understand this incredible system that is Bitcoin. And and you follow with us our explorations, and that is the value I think this show gives. It's different from other shows. Stephen, you are free to add whatever you like to this.
Well, just on follow-up for content, I often, not always, but usually try to write a Substack article that's related to the content of this show. And then I provide the link to that over on X, Twitter as well. So that's one other way to kind of look at it, read about it, what we present on the slides, and understand a little more deeply.
Yeah, so follow Stephen. I did write myself several articles on some of the subjects, and you can also read them. And I will try to add actually even retroactively to our old episode. In fact, this is episode 19. We did 19 of these episodes so far. So you can actually follow both of us on X and Medium, and you use mostly Substack, right?
Yes, I'm now focused mostly on Substack.
Yeah, I should also transfer to Substack, or at least both.
Yeah.
And so we go a little bit deeper, so you can. But one of the things that we are going to do also in the show since now on, in fact, today we are going to do that for the first time. We're going to look at some of the papers because actually, I don't know if many people know that, but a lot of serious scholars are actually studying Bitcoin scientifically. So it's not just the two weird people like us that we decide, oh, Bitcoin should be studied scientifically. It's studied. There are publications. Some of the publications that we are going to talk about, we're even publishing physics journals. I'm not sure if this one was, but the same author that yeah, exactly. So different physics paper, different economics papers. So there are probably hundreds of papers written on Bitcoin. It's still a nascent field of study, but people take Bitcoin seriously and write scientific papers. So one of the services that we will offer, in the future, will also be to discuss some of these papers, trying to summarize them for the audience and explain what they found. That is not necessarily a particular angle, but different interesting angles. Stephen, you can go ahead.
I want to add just a little bit on that.
Yes.
We have shown references to some of the papers. Most of the papers that are written by people who have a finance or economics background. And so they tend to approach it with the traditional tools that assume, things like log normality and reversion to mean and so forth. And we've referenced both when we did analysis about skew and kurtosis, and also when we did analysis of the Hurst exponent, which is the persistence of Bitcoin behavior over long times being very high. We've referenced other papers, and we've found that we believe they have shortcomings because they're not aware of the power law. So what they do is they do their residuals in the traditional way instead of taking the power law first out for the residuals. And it makes a very large difference. So you can go back and look at some of the other episodes and drill more on that.
Right.
And with that, I think I'll dive in and put my screen up if you're ready, Giovanni.
Perfect. Yeah, absolutely. Great.
Okay. No, that's the wrong window. Hold on a second. That one.
Okay.
All right. This is indeed number 19. And today we want to talk about a couple of papers from a physicist. His name is Didier Sornette. He's based in Switzerland. He's a professor emeritus at ETH Zurich, which is kind of the top university in Zurich, basically. And the particular paper we're going to focus most on was just published earlier this year. And he looks at the distribution of holding times, how long people hold before they sell or trade or whatever. And there's also reference to another paper that was written, I think in 2020. We'll show when it was written, but I think it was a few years ago, where he has a hypothesis about social bubbles. So we'll discuss that one as well. But so here's the agenda. First, I'm going to start out with a discussion about astrophysical shocks, and it will become clear why in a moment. And it kind of relates both to some of his work and even this social bubble hypothesis, but it also relates to a question that I saw on Twitter and responded to there and in here. I'll talk about the Pareto, which is another power law for wallet sizes, talk about that briefly, and then get into this paper, Sornette and Zhang, written with a co-author in China, and first written in 2024 and finally published in a physics journal earlier this year. And one of his findings is that traders perform suboptimally. It's not surprising to us who've been in the field for a long time. It's always true. It's true in the stock markets that traders perform suboptimally. It's impossible to perform optimally, but I think he would say highly suboptimally. And he did some very detailed analysis on the blockchain and when transaction balances move to substantiate that. And he finds that holding times follow this fat-tailed power law. And then I'll close with this social bubble hypothesis discussion. But the first, I wanted to respond to this question that someone asked on Twitter. If there were no bubbles, would there still be a power law? And I've got an analogy here, which is based on some astrophysically motivated research. This comes out of China from the University of Science and Technology there. And so what they did was in the laboratory generated plasma and shocks in the plasma in order to simulate what's happening in astrophysical shocks, astrophysical plasmas. And so they use the lasers to accelerate what they call the piston ions, and they slam those into the ambient plasma. Now, this plasma is collisionless. It's not like these ions are hitting each other because the density is low. But what happens is, because everything's ionized, all the electrons have been stripped off. So you've got electrons that are free, and you've got nuclei that are, positively charged. But it's the electrons that are defining the electrical and magnetic fields in the environment. So we can think that our analogy would be the piston is the power law, is the driver of things. And what they find in this laboratory experiment is that the piston ions are moving at one velocity, which is around almost 500 kilometers a second. But because of the fields that are generated, those accelerate ions. And actually, the ions and electrons have to accelerate together because you have to maintain roughly, neutrality and charge on the larger scale. And those get accelerated to 1,250 kilometers or so. It's about a factor of 2.5 times higher. So the fast ions result from this piston acting upon the ambient conditions. Now, if we look at our Bitcoin residuals, this one's for gold, but it's similar when you do Bitcoin against dollars. And if you've attended some of the previous talks, you know that Bitcoin's distribution is bimodal. The residuals, which is what we're showing here, we're showing the log of the residuals on the x-axis, and then we're showing the frequency on the y-axis. And you can see that it's a bimodal distribution. In fact, it's more or less bimodal Gaussian, two Gaussians that are overlapping. And the separation between those two is this same factor of 2.5, kind of coincidentally or interestingly, as they found between the piston ion velocity and then the fast ions that got accelerated by what's called Fermi acceleration mechanism. And just their two charts are just the experiment on the left and their simulation on the right, which match the experiment pretty well. So there's a similar separation factor between the core and the bubbles in Bitcoin. The power law is why Bitcoin is anti-fragile. It's why it has succeeded. It's the foundation for everything. And when the turbulent flow ends, or when you stop, shocking the plasma, you're still going to have continuation of the underlying flow, which in our case would be more ordered, more laminar kind of flow. Also, it's important to note that the bubble sizes are falling as nearly the inverse power of age, somewhere around the minus 0.8 power of age, perhaps a little bit more steeply. So the bubbles have been fading away, but the power law has been persisting more and more. The persistence exponent, as we measure with Hurst, has not gone down. The R squared that we measure in the regressions goes up. So the answer to this question is yes, there would still be a power law. Now, there's a power law in the wallet balance distribution, and this has been known for some time. And I know you've shown this before in different contexts as well, Giovanni. This is showing the number of wallets versus number of addresses or wallets versus how much is held as a balance. And these bins are an order of magnitude each. So kind of a big jump, but each bin is a factor of 10. And the lowest one that I plotted here is the bin that is between 1/1000th and 1/100th of a Bitcoin. So, it's between 90 something dollars and almost $1,000. And the X's mark the geometric mean of the bin. So it's something like, if it's going from 0.01 to 0.1, then it's around 0.03, because that's the geometric mean. And also, things are going to be distributed more towards the left side of the bin. And then you do a regression through that of an inverse power law. And it has an index of 0.82 or minus 0.82, actually. And the R squared is 0.95. And it works quite well across the bulk of the range. But when you get up to 100,000 Bitcoin, then you can see that it's falling off away from the power law. And we know that eventually it has to cut off because they're just limits. It's very difficult to own more than 1 million Bitcoin, right? And certainly 10 million is going to be impossible. Even Saylor's not going to be able to do that. So there's an exponential cutoff at the high end. It looks like there's a flattening at the low end, but for the bulk of it, it follows this Pareto fit. If it were -1, it would be called Zipf's law, but Pareto's more general. It allows for any value of the exponent, but it talks about how frequent things are relative to scale. And it applies to lakes and many other things as well as wealth.
By the way, I think the pronunciation is
Yeah.
Pareto because it's Italian.
Of course. Thank you.
Minor detail, but it's
good to know. 66 wallets have more than $1 billion currently, and the largest 91, almost 100 wallets have almost 3 million Bitcoin. So we know that there's a fair amount of unbalance in the Gini coefficient sense. But I'm not going to drill any further on that for now, and we'll get into Didier Sornette and his work. And he's a very prolific author. He started out in geophysics, and he started studying, earthquakes and then avalanches, and he found way to model things that are in a kind of crisis state and the way that grows. And it's called an LPPS model. It's actually shown in this lower right-hand figure, how Bitcoin bubbles scale, but we're not going to talk about in this show. However, if you want some exposure to that, you can look at his video, and I've got the link here. I think you can just search on ETHZ and Sornette and find that. And in this video, which is actually on the ETHZ website, he talks about 3 topics, and we're going to look at the first 2. One is the dynamics of Bitcoin transactions and prices, and the second is this social bubble hypothesis. Okay, and here's the paper. It's in Physica A, which is a European physics journal. The title is Transaction Flows and Holding Time Scaling Laws of Bitcoin. He's the first author, and he's got actually, since he's retired from ETH Zurich, he's got an association as well, I think, with this university in Shenzhen somehow, and with a couple of other universities. And he has studied a lot of different phenomena and particularly interested in bubbles and crashes. And so he's done a lot of work in finance and includes a number of papers, probably half a dozen papers related to Bitcoin and to some extent cryptocurrency. Here are 3 key statements from the abstract. First, that the average distribution of holding time is a heavy-tailed power law that extends to at least 200 weeks and with an exponent approximately equal to 0.9. And so there are clearly very long-term memory effects in there. And then he finds, shorter term, there's more variation depending on the Bitcoin price regime. Holding times get shorter as we're in bubbles, right? And then they document significant differences between the distributions of book to market and realized returns showing that traders obtain far from optimal performance. And we'll show a graph from his paper that visualizes that. And then also he finds that there's a power law dependence of the time average transaction flow as a function of age, and the exponent is similar to what is found in priority queuing theory, which is a minus 1.5 exponent, or minus 3 halves. Okay, so this first one is actually the fractions held in different time bins. So there's the Bitcoin price curve in blue. That's a logarithmic price curve against a linear time scale, and it extends into 2022. So they did deep blockchain analysis of all the transactions well into 2022, but not since then. The orange curve is short-term holders, which they define as less than 1 month. The green is medium, which is up to 1 year, or between 1 month and 1 year. And the red, or kind of reddish brown curve, is longer than 1 year. Or you can call this smart money, dumb money, and dumber money. Because what you see is two things. One is that the total fraction of Bitcoin held by smart money has risen from 0.3 to almost 2/3, from 1/3 to 2/3. And that the total fraction held by the dumb money, the green curve, has fallen from 1/2 to 1/4. So the smart money doubled its Bitcoin balances, right, in terms of percentage of a rising supply. And the dumb money, its balances were cut in half. And roughly the same thing applies to the dumbest money, which is the orange. And what you can see on closer inspection is, for the orange and the green curves, that they buy more when the price is rising, and particularly as it's going up into the steep part of the bubbles, the orange guys are buying quite rapidly, right?
Randomly, right?
Rapidly.
So the smart ones, tell me if I interpret this correctly. They tend to buy when the price is low, and they tend to sell. So maybe rebalance a little bit their amounts.
Yeah.
At the top, right?
It's very clear. So look at the first one, which is the 2013 bubble. So they held, not quite 0.5, and then they dropped down to, high 0.3 something. So they sold into that 2013 bubble that peaked at the end of the year in 2013.
Yep.
And then they started buying again, actually early. They bought it as it was declining, and they kept buying, and their buying increased very rapidly as it was not quite at the bottom, but approaching the bottom. So they were really finding value. And then they kept buying even after that, but more slowly as it started to rise again, and then they peaked.
Yeah. This is an amazing graph. It's actually one of the most important graphs I ever seen about Bitcoin, because which more people look at these, right? When I understand people want to hold forever, and that is great, but somehow these long-term investors, they kind of follow what the market does, right? Of course, they could be the ones that actually make the market crash when they decide to sell, but they do the smart thing. They sell when, and they do it gradually, right? They never do it at one single place. They start to balance, right? Rebalance their portfolio as the price goes up. They rebalance, like some of the things that you talked in the past, right? It's not too bad of an idea to have a mixture of cash, for example, maybe gold and Bitcoin, and then as the price increases, they rebalance, and that eventually actually that works, because you can improve your position doing that, right? Is this your interpretation of this graph?
Well, precisely. And you see that it works repeatedly, because there are 4 instances where they peak, and there are 4 instances where their curve, has a minimum and troughs, and they were right every time. So they were 4 for 4 generally when the price was high and overextended, and they were 4 for 4 when it was low and a value. So they buy low, they sell high. But they don't sell out completely. They're long-term hodlers as well. They keep growing.
Yeah. And the dumb people that are the medium, right, and the short ones even less, right? They do the opposite. Just they buy at the top because maybe they get in because of the FOMO and everything, and then they get scared and they sell at the bottom or close to the bottom, right? So,
Right.
and the total result is that their positions actually are going down, right? In general.
Right.
Yeah.
Right. And so most of the balance is held either in the smart or the dumb. The dumber doesn't have that much of the balance. So that also says that on average, people have been extending their holding times. There's not as much of this, under 1 month trading as you might think.
Yeah.
Okay. Then the next curve, somewhat similar interpretation. It's the probability of a sale. This is a log chart. So the probability is a log on the y-axis, and the time scale on the x-axis is in weeks. So you've got, from 1 week to 200 weeks, and it follows the power law quite closely. It's a minus 0.87. And since the absolute value is less than 1, it means if you were trying to integrate under this curve and took it all the way out, that it would diverge. It wouldn't converge as an integral. In other words, it's falling slower than a reciprocal, which is a 1 over time scale law. But we know that there's a cutoff because, we've only got 750 weeks or something of total history, right? So there has to be a cutoff out there, but it's beyond 200 weeks. So they say we've got cascades of social interactions. This is quoting from their paper. Up to a time scale, which is long, the system behaves in a critical state to greater than 200 weeks. And he calls it a extremely wild regime. Heavy-tailed. Heavy-tailed means the slope is relatively gradual, not steeper than reciprocal. And so a significant fraction hold for very long times. And we all know that from, our experience being in Bitcoin for however long we've been. And you can look at the correlations between short, medium, and long-term holdings, and it just sort of summarizes what we saw on, 2 graphs ago, which is that the correlation between short and medium is positive but small. But for the long-term holders, greater than a year, they're highly anti-correlated with the short and medium-term holders. So long-term holders buy value, sell into rises or rebalance because they don't sell out completely. And short and medium termers buy rises. And the next one is his paper from 5 years ago, 2020, almost exactly 5 years ago. And he presented this social bubble hypothesis. It was called Boom Bust in Bitcoin. It was written with one of his co-researchers, also probably a student of his at ETH Zurich.
Mm-hmm.
Bitcoin bubbles as innovation accelerators. So I want to agree with this in part, and I want to disagree with it in part. I think I'll read his abstract. Bitcoin represents one of the most interesting technological breakthroughs and socio-economic experiments of the last decades. In this paper, we examine the role of speculative bubbles in the process of Bitcoin's technological adoption by analyzing its social dynamics. We trace Bitcoin's genesis and dissect the nature of its techno-economic innovation. In particular, we present an analysis of the techno-economic feedback loops that drive Bitcoin's price and network effects. Based on our analysis, we test and further refine the social bubble hypothesis, which is, his name for something, which holds that bubbles constitute an essential component in the process of technological innovation. We argued that a history of repeating an exponentially increasing series of bubbles and hype cycles, which has occurred over the past decade since its inception, has bootstrapped Bitcoin into existence. So I'm going to agree in part and disagree in part. I agree that bubbles help promote the innovation and adoption. I do not believe that bubbles bootstrapped Bitcoin into existence. So I disagree in particular with that final statement. But I agree with the concept of bubbles as chaotic attractors that he talks about in the text of this article. I would say that existence and success come from Bitcoin's first mover advantage, its pristine nature, its decentralization, its impeccable design, and the very high energy input and very high hash rate enforced security, and of course the absolute finiteness in supply that led to social network adoption. And all of these things contrive, along with the feedback loops from the meta network, contrive to give us a power law. So I would say that bubbles helped anneal Bitcoin's anti-fragile nature, but the bubble power falls close to the inverse with age. The power law is stronger than ever. In his analysis, he did not note that the bubbles are decreasing in relative intensity. I call him Dr. Bubble because he's a world-class expert on that. So it's natural for him to think in terms of bubbles. But I don't think he noticed that the bubbles are falling in intensity either in this paper or in the more recent 2025 one.
Mm-hmm.
The power law core is the fundamental nature. Bubbles right atop that, and we've shown that.
Right.
Any comments, Giovanni?
And they could be something that I still want to explore because for example, that it turns out, and we discussed this, but it's something that I still want to understand myself better, that bubble are actually log periodic power laws with a complex exponent. What that means, what is the concept? Because in a sense, that tell us that there is some kind of continuity, right, between this turbulent flow, like you describe it, and it's not really two completely different phenomena. They interface, right? There is some kind of interface between the two, and it's possible that as the bubble became smaller and smaller, they are still there, but we don't notice, right? Because they are smaller, and so we don't call them bubbles. But they should still happen at all levels because it's kind of a fractal phenomena. One of the things I remember, I don't know if I told you this story, when I was doing neuroscience, I was studying these nonlinear features in the human brain activity that are called slow waves. They are features that appear during the deepest phase of sleep. In fact, sometime I will make a little presentation of that because I think it's relevant. And when I was studying them, the first thing I asked to everybody, I was working in the neurology department, so most of my colleagues were not physicists, were doctors, very good doctors, world experts in their field of neuroscience of sleep. But I asked that natural question. I say, do you know of any publication where the characteristics of these features, like, for example, their amplitude, they look like sharp ripples, they last very small amount of time, maybe 5-6 seconds, and they seem to oscillate, and they have amplitudes. And I wanted to know, it seems pretty stochastic process. I wanted to know if anybody have studied the distribution of the amplitude, of the duration, whatever characteristics, because as well as me, that as a physicist, by studying the distribution, we can get clues about the process behind them, right? If we have a long tail, for example, if you are Gaussian or whatever. And almost everybody was telling me, no, but probably they're a bell curve, right? around some kind of an average. And it turned out they were not. In fact, this is for the people who even understood what the distribution was. Like many of them didn't even have a clue of what I was talking about. And it turns out there is this manual, right? Because doctors like to do things by the manual. They write this manual, somebody takes charge, they write all these rules, like a little bit like lawyers, right? We like to have rules, to go by, because when it became standard, this manual is distributed all over the world and everybody follows the rules in the book. So, for example, when they score the sleep, right? If you go to one of these sleep labs and they do a study, right? A sleep study, and they tell you if you have problems, if you have apnea. They look at 30 seconds of data. That, by the way, that comes from, it's like an anachronism, because it turns out is how much paper you needed when you added these ancient systems with the needle, and this how much you could fit in a paper that you can actually hold on your table, 30 seconds of data, and we still use the system. It's very artificial because, there are no 30, the brain doesn't know about 30 seconds, but they still do that. And they call it, they call it epochs. So they tag them and they give a number, 1, 2, 3 for different depth of deep sleep, and then they call it REM, if it is REM, or awake, if you are awake or whatever. And the criteria for identify these waves, and so what determines if you are in deep sleep, because they literally count. They say if you have a certain number of these waves in 30 seconds, then you are in deep sleep. But what defines as low waves, according to this manual that is used all over the world, is a threshold. They use a hard threshold that is 75 microvolts. If the amplitude is bigger than this, then it's a slow waves. But when I actually went and studied them in a systematic fashion over many subjects, many ages, and I released this constraint and say, let me collect them. There are ways of identifying them beside the threshold, right? Their shape, their duration, their frequency. I collect all of them and I say, forget about the threshold. Let's see how they look like without a threshold. And you know what? First of all, they were not normal at all. They were log normal. So they had an enormous tail. And the 75 threshold was all the way to the stream of a tail. That is ridiculous. It's basically like saying human beings, only 6'5" human beings are human beings. Just the tallest possible human beings are human. Everybody else is not. When the average is much lower than that. Normal human beings are not 6'5". But the human eye can catch these large features, and so they decided that was the threshold, something large, right? Because human beings, we are not able to understand scales, right, in an intuitive way. But we were slow waves that went all the way to 1 microvolt, right? 1 order, 2 order of magnitude smaller than the cutoff, because they were uniformly distributed. They were all over the place. You had a very, very small little slow waves, that you would never have considered slow waves if you stuck with this threshold. So I'm telling you this story because, I think we do something similar here where we see this huge big bubble and we recognize them and say bubble, but bubbles happen at all levels, right? That it could be an hypothesis. In fact, it's something that probably we could study with some kind of general definition of what we can consider a bubble, maybe a fast movement up or whatever, and then look at their distribution. I'm pretty sure if one did a study like that, he could show that it's a uniform distribution, probably with a long tail, like these slow waves, So it's just that, for example, when you age, these slow waves are becoming smaller and smaller, and maybe there is something similar to this. The system is not young anymore, and it doesn't have this. It's much more. I don't know. There is some process that makes the system more consistent, more reliable, and this large events are rarer, than when you are young, for example.
There's capital sloshing around in a basin, and it's getting deeper and deeper, right?
Exactly.
And so the relative size of the surface waves decreases, even if they're the same absolute size. In dollar terms, in logarithmic terms, or on a log linear chart, they're going to decrease. So
yeah. And what do you think about this bootstrap Bitcoin to existence? You don't buy it, right?
I don't buy it. We didn't need Bitcoin's existence was bootstrapped by the existence of a network and the design. I think the bubbles annealed it, but that's not existence.
No. Yeah, and it's an interesting idea, and it could be maybe tested. That we could do some more rigorous testing about that, but it's probably some kind of a feedback loop. I'm sure of it where many people that join during the bubbles, right? But and so they played a role in that sense, and so historically maybe they were important, right? It was important to have the bubbles.
Yeah, my take is all they did was help it overshoot the power law. So it overshoots the power law, but then it
Yeah,
returns to the power law.
right.
So the power law core is the fundamental nature. So yeah, they run in, they FOMO, and it overshoots the power law. But then out of necessity, it's unstable,
Yeah,
as Sornette has always shown with many phenomena, and it collapses.
yeah. And we
You
saw
know,
from the previous graph that yes, there are a lot of people that joined during the bubbles, these short
and then they leave,
investors,
and then
and
they
then they
leave.
leave. When they leave, right? So it could be actually maybe even anti-productive. It's something that needs to be explored. Actually, it could be an interesting thing to do because it's almost like he's contradicting himself, right? In one paper he says
Yeah,
this,
a little bit.
and the other one he shows that actually long-term investors avoid the bubbles. They get out of the bubbles, and then they join when things calm down. And the short-term investors do the opposite. But I don't know.
I think it already manifests itself when you plot the power law index as a function of age,
Right.
and you see that it rises above the long-term mean initially quite substantially, and then it falls below the long-term mean,
Right.
and then it oscillates and it locks in, and the oscillations become smaller. So I think that shows you an annealing process.
Can you explain to the audience annealing, what annealism means?
Yeah, annealing is what you do when you change the temperature. Like when you make steel, you heat it and you put it into a cold bath, and then you heat it up again and put it into a cold bath. And then I don't know anything about the chemistry of this stuff, but the microstructure in the steel gets hardened by this process
Right.
of raising temperature and lowering it. And so this is used a lot in something called simulated annealing, is used in algorithms when you want to run optimization problems. For example, you want to find the minimum, a global minimum of something that's a very high dimensional space. So it's very
Yeah.
difficult search problem. What you do is you raise the energy level, temperature, quote unquote, so it's like the ball's rolling up the hill and then it has to roll down into another minimum. Is it the right minimum? And by raising the temperature, you allow the ball to then go roll into other hills and valleys, and search for these different minima. So annealing is this process of hardening something towards the final optimal situation or configuration.
Yeah, it's you're basically avoiding local minima, right? You're trying to find like the best configuration for your system by stressing it, right? You're pushing
Yeah.
it and it's a beautiful analogy. In fact, actually, something that should be explored more, I think, because it's basically like it's when there are many people that tell me what happens if Bitcoin, the power law is not followed anymore. And I tell them all the time that happened many times in Bitcoin history. In fact, every time we had a bubble, we left the power law. It was a kind of a stress test for the power law. And that is a very similar to this idea that you're showing it's like almost we test it. In fact, actually it was a good thing because we release, it's almost like a relief valve. We release a lot of this energy, maybe it was people got excited because of a halving, mostly psychologically, there was a wave of investment. So some of these social bubble hypothesis could be right in the sense that it was almost, like, call it the Christmas, Bitcoin Christmas, right? People knew that there was this event, it was significant, the news talked about it, etc. It was a wave of investment, and it created stress, and that stress produced FOMO, it pushed the system, it pushed it too far, and the system corrected itself. And so it's actually a very good idea, because one of the purposes of, people see this in the movies, right? When they forge the magic sword or something, right? And the smith puts the sword in the fire, makes it very hot, and then he plunges it in the cold water, And the reason you do that is because if there is any stress, any fracture in the material, is getting released when you're eating it, because all the molecules are moving around, and that energy is released and distributed. And then you cool it and you freeze it, right? It basically, you recrystallize the material, and if you do this over and over again, you make a material much stronger. This process is called annealing in physics, and you actually can even write equations and show it's like a cycle. It's a process, and maybe this is what the function of these bubbles have been so far. And the fact that we don't have these huge big bubbles anymore is telling us that the sword is getting stronger and stronger. You don't do this process forever. After some cycle, after you do it a few times, it's kind of a diminishing return process. And at a certain point, there are no stresses to be released, and you just have a fantastic sword, And this is what.
Yes, and then you're ready to attack the fiat system with it.
Exactly. We are making this katana, using this fantastic process, and I love it. Idea. I think actually maybe it could be like a paper that we could write about this topic, right? Almost as an answer to this paper. It's not really a contradiction; it's an elaboration. It's an improvement on the paper, because they played a role, but it's not exactly the role that they mention here. It's mostly like almost like a stress test. It was a kind of a release system, for stress, for different tensions that we had in the system, and and they became smaller and smaller, like it should be. In fact, even these slow waves are very similar to that. One of the reasons they exist is because they play a lot of functions, but one of the functions is to release, to destroy all these toxins that we build up during the day as a process of our metabolism. And as the night passes by, you see the amplitude of the slow waves became smaller and smaller. And they also happen in cycle, because we have these cycles of about 90 minutes where we spend some time in deep sleep and REM, then we had another bout of slow waves, and every cycle became smaller and smaller and smaller. So actually, and this seems as a silly analogy, but it's actually, again, it's a very similar process, because there is a lot of complexity. They look at like avalanches, these slow waves. They are networks, because we have. So maybe it's a one-to-one analogy that it could be explored, could be very interesting to explore. It's one of these things where in physics we put them in this big basket that we call it complex systems. So, it's a very interesting topic. So we call it also self-criticality, this entire idea. And Bitcoin, it's in fact our hypothesis that it falls in these categories. This is why physics is so relevant in understanding Bitcoin. So maybe this is the role of a bubble, to be this annealing process. I love it. It's a very, very interesting idea. Should be explored.
Okay, so that was my last slide, except to thank you for watching. If there were no bubbles, would there still be a power law? George C. Scott from Dr. Strangelove, has he got a chance? Hell yeah.
So cool.
Okay.
All right.
Stop sharing if I can get my mouse to work.
I'm going to share my slides if I find them. Okay, and we don't have a lot of minutes, so I wanted to do a little market recap, but let's do first my demonstration about Metcalfe. And then maybe if we have a few minutes, we can talk about the market. All right. Yeah, so first of all, this is not related to my slides, but it's a book that I suggest to everybody. So, one of the reasons why we do this show. And I know that people would make fun of me all the time because I have a PhD in physics, but I'm not able to do a presentation. Believe me, I'm trying. I'm saying, go under slideshow, and they say, slideshow from the beginning. Does it look better? No. But anyway, I'm trying. This is a book that Sornette wrote, and it's meant to be general reading. It has a little bit of math, but it's a very beautiful book if you want to understand the market in general. But look at its title: Critical Events in Complex Financial System. Right, this idea of complexity theory, that is all about these nonlinear processes, etc. This entire field that I explained, that covers so many things in nature, and so he's applying this idea to physics. Sorry, to financial markets. So when I hear that all the time, people say, "Oh, what physics has to do with financial market?" A lot. People have wrote entire books like this, and they have applied it to, to different investing strategy and hedge funds, etc. Right? One of the most successful fund in history was run by a mathematician. He also contributed to physics, and it was called the largest physics and math department in the world because it was full of PhD in physics and mathematics. In fact, a lot of physics department complain that so many clever people they got PhD in physics go to finance. So it's very relevant. It's just the people that don't know that this is happening that make this kind of complaints because we are not aware of this. But this is a beautiful book if you want to go a little bit deeper in this topic, and he explains this approach. We are going to explore it more in the future. In fact, I want to even to make a kind of a app that people can use about these log periodic power laws, because they are supposed to identify times when people kind of organize themselves, and this is why these analogies with earthquakes, financial crises, failure of materials, these techniques have been used. We were talking about stress before to identify cracks in vessels, for example, like NASA hired Sornette to apply some of this technique to find little cracks in fuel tanks that could be catastrophic, right? If because they can lead to explosions and things like that. And so, yeah, he's using the same ideas in understanding financial patterns, and you can use them to predict ahead where a certain it's mostly not necessarily a crash. It can be also like a run up, like the beginning of a bull run. You can use it in both directions. So it's something that eventually we already have an episode where I did some talk about them, but we can go back and explore. This entire topic is called log periodic power laws. It's not exactly the power law that we are discussing when we are discussing the general trend, but it's somehow related. They are kind of related topics, but we will discuss this in future times. Maybe even we can talk about the book, right? This could be another episode where we kind of break down some of the ideas of the book. Anyway, so what I wanted to cover tonight, and by the way, I wanted to announce also we are working on creating this institute. We already mentioned before, me and Stephen and other people are coming together to create this institute. But the idea will be to study Bitcoin scientifically, because we think that Bitcoin is so interesting, so regular, etc., that it's worth it to be studied scientifically. So we are going to create an institute. Eventually, as the institute grows, we will have conferences, papers, and maybe even scholarships for our students who want to study Bitcoin and maybe write a dissertation, a master thesis, or maybe even a bachelor project, a capstone project or whatever. So it's this is what it's a very interesting idea, and we will discuss it more. But I wanted to kind of give you a preview of this development that me and Stephen are working on. But this is relates to some of the posts that I did in the past, but I wanted to discuss them in the video today in our show. So there is this question, right? So we found all these power laws, and one of the most fundamentals, in fact, is one of the first power laws that I found. By the way, Sornette has a paper that we can also discuss in a future show, where he mentioned the Metcalfe law. They found the Metcalfe law themselves. They found it 4 years after I mentioned that there is a Metcalfe law in Bitcoin. As far as I know, I was the first one mentioning, but I did this mistake where I will post on social media, in this case, Facebook and Reddit. I have Reddit posts. Some people nowadays, they even use Reddit post as a reference, to quote other people's work, but at least maybe Medium articles and things like that. But I cannot ask for a scholar like Sornette to go and search Reddit posts, right, about Metcalfe law. So it's okay, But I came up with this idea before Sornette show. But it's good that they verify that is the case, that there is a relationship. So what is the Metcalfe law? The Metcalfe law basically says that if you have a network, the value of a network, and value could mean many things. It could be the monetary value, but also the utility value. How useful this network is. It's not really in the nodes, right? This is kind of you see here, a kind of simplified version of a network. Networks have two main characteristics, right? I mean, two parameters, two things that create a network. You need nodes, right? Here the pin of these needles, and then you need connections between the nodes. And nodes it's basically it's whatever centralized little entity that does some kind of a process in network. Usually there is some kind of decision making happening there, some kind of an action, some kind of event, or some processing of information. So if you're thinking about a bunch of computers that are connected, they do something, they process information, or they do some kind of a calculation or whatever. And in the case of cells in a body, they are physically processing materials, like proteins, etc. Then they exchange some information between them, right? So they are individual entities, but connected somehow by links, right? These are called links or edges. The technical term is edges. And this engineer Metcalfe made a kind of a prediction, because we didn't have a lot of data about network. It's a nascent science. But by the way, many physicists contributed to network theory. One of the most important network theory physicist called Barabasi. Is from Bulgaria, I think. And this Metcalfe said that the value of a network, the utility, the value, if there's a monetary value, you can actually, it's more easy to measure it. It's proportional to the links. That really what matters is not the individual. So it's not many nodes you have. Of course, more nodes you have, more links you have. But if you have a few nodes and they are well connected, they can be as valuable as some network that has a lot of nodes that are not well connected. And it turns out if you have 10 nodes and you connect all of them, every node is connected to every other node, you can show as you make the nodes. The formula is a little bit more complicated for a small number of nodes, but if you make the nodes more and more, you can simplify the formula, because we like in physics to approximate things. You can approximate and show that is proportional to the square of node, the number of link in a case where everything is connected to everything else. And you can, if you are curious, I can tell you very quickly how to arrive to that number. Basically, imagine there are 100 nodes, right, or something like that, and everybody is connected to everybody else. So how many, if you are one node, how many other nodes can you connect to? 99, right? That is everybody else. Okay, so it's you, because it doesn't make sense to connect to yourself, right? So you connect to a 99 nodes, and that applies to everybody, right? So it's basically 100, close to 99. So it should be n, the number of nodes, multiplied by n minus 1, right? That gives you n times n minus 1 is n squared minus n, right? But if you make n big, n squared is much bigger than n, so you can throw away n, right? Something that many times in physics we do. Because, imagine you have 10,000, right? You take the square, you get 10 million, right? And 10 million is much smaller than 10,000, right? This is much bigger than 10,000. So you can throw away the 10,000 and stick with the n squared. This is why it's n squared, right? It's very simple calculation. And it's funny because one time I saw this interview, maybe I link it when we publish this video on YouTube. There is a lecture that you can find of Metcalfe where he was invited somewhere and he talks about the story, how he did it. He's also the inventor of the Ethernet. And when he came, this was the early days of the internet. And literally, you had to buy a piece of electronics, like a little feature, a little electronic piece with transistors and whatever, and you had to insert it, or you have your IT person inserting it in the computer, almost like a graphic card today, right? If you have a fancy graphic card or some extra memory, you have to insert it inside the computer. You had to do that with electronics that allowed you to connect to the internet, both the nascent internet that we were creating it at the time, but also if you want to connect to a computer internally, right, inside a company, a university, some kind of organization. You had to buy the little physical piece, and he was selling these physical pieces for $1,000. And companies were buying 1, 2 at most. And then one day, because I think engineers are also business people, right, he came up with a very clever marketing idea. And the marketing idea was, I'm going to tell everybody. But he was not just a salesman, he was also an engineer, so he had to stick to reality, couldn't tell them a lie. It's true thing, right? He was saying, well, think about this, right? If you have more computer connected, so you buy a lot of these little pieces of electronic, let's say you have 10 computers and you buy one for each of them. I know it sounds a big investment, but actually you're getting much more out of it, because all of a sudden now your value it's 100, because it's going to be the real value that you're buying is not the number of units, but all the connections that you can create between all these people talking. Maybe you can have emails where they can talk with each other and they communicate, and then all these computers can also connect to the printer, and eventually when the internet comes, everybody can go to the internet, and you can increase productivity. You get much more value. One process is linear, how many of these units you need to buy, and the value goes square. So the value will catch up, right? It will be much better investment. So it was very clever idea, right? But it's also an interesting proposal that networks grow their value in a non-linear fashion, right? You get much more by connecting everybody. And the idea is that why this will apply to Bitcoin, right? We use this word loosely, that Bitcoin is a network, etc. But we have evidence, right? And of course, with the power law, we think we have evidence that actually even price discovery is determined by these properties of network. So we claim it, and we see evidence, right? Because we see this was one of the first power laws that they found, that if you plot the log of price versus the log of users. Now, we don't have users. We use addresses as an indirect a proxy for users. We see this straight line. And the straight line slope that gives you the power, it's close to Metcalfe. So Metcalfe, remember, says square. And what we observe experimentally is something like close to 1.8 or 1.76 or something like that. So it's not perfect. It's not a theoretical result. And you will never expect to get the theoretical result from a real system. But it's kind of interesting that it's close to 2. Now, I saw a post some time ago where Fred, for example, I like a lot of things from Fred. He's a mathematician, etc. But sometimes he makes some statements that I don't know where he takes this statement from. But he say, I think it's a coincidence. And it's not a coincidence. And you can actually make an argument that it's based on, logical and theoretical arguments. And this is what I'm trying to do here. So I'm saying, when people try to establish the price for Bitcoin, it's not that they go to the market and they look at the price and say, I'm going to buy a bunch of Bitcoin, right? There is a process. We know that, right? We call it orange pilling. People do this DCA, etc. And it's all based, of course, on how people feel. Do they feel excited and they want to buy? They feel scared and they want to sell, right? You saw what happens with that graphs, right? They tend to sell, the long-term holders sell at the top and so on. So this sentiment is guided by interactions with other Bitcoiners, because you watch this video, all these people that are watching this video, I just checked a few minutes ago, we were close to several hundred, sometimes you have 1,000 people. There are 1,000 people watching this thing at night, and different parts of the world. You don't see a lot of people doing that with other assets like NASDAQ, etc. Right? We are much more passionate. We are much more interested. It's something that it's really a social network. There are a lot of interactions. People listen to influencers, educators, sailors. There are these financial institutions, and it's something that is much more integrated, and there are all these network properties that are influencing how people decide how much they want to spend on Bitcoin. So that is an hypothesis, right? And but the interaction, the level of interaction and influence, etc. Somebody that has a YouTube channel will have much more influence, because if I start to say, I think we are going up, right? As small our channel is, we are going to influence a bunch of people that the single individual cannot do. So there are different levels of influence. That is the other hypothesis, right? And so different levels of involvement. And these interactions are not, so this is the other hypothesis that we are saying, they are going to be multiplicative, right? Because you influence 2 people and these two people influence other two, and then these other two influence. So it's a multiplicative effect. It's a non-linear effect. And so, and this I gave an argument. Probably this will be eventually maybe even a paper. But basically, we are saying, imagine kind of like a Metcalfe proposed that the value of a network is proportional to the number of users, right? And these number of users have some kind of activity level that we call phi, right? In this case, that is proportional to the number of users. So when you add one more person, every time you have one more person, you're going to increase this activity by some quantity phi prime. This means the change. So this was the activity before we added one person, and this is when you add one more person. And like I say, the value of the level of interaction, how powerful this new activity is, how strong this new activity is some kind of probability process, right? It's going to be random. Somebody is going to have to be very influential, somebody less influential. So this is what we are writing here. And this prime, remember, is a change, right? So these we can.
Giovanni,
Yeah.
sorry, your slides are not advancing.
They are not advancing.
No. There you go. Okay, now you've got
it. Strange. Okay, and this was the one that I was showing before, where I was talking about. So maybe you didn't see. I don't know what happened. I did a slideshow and I was scrolling, but maybe I need to go out of the slideshow. Maybe my setup. I will check it out. I don't know what is wrong with this setup. Anyway, so it's a probabilistic process, right? Where when somebody new comes in the network, some new user, their level of activity is proportional to some kind of probability value. So it can be between 0 and 1. And then because this phi prime has to do with change, many times, in physics, we use this terminology, this we call it a derivative. So we're looking at the change in phi relatively to the change in n, so the number of users. And we write it in this way, right? So to solve it, you will have to solve this equation, this exponential, because this is called a differential equation. When you have an equation where you have on the left the change of a parameter, that is 5 in this case, that is related to the parameter itself. It's called a differential equation. And there are many techniques to solve it, but many times I remember my first course in differential equation, my professor told me, just guess it. That is the first level way that you can solve an equation, because that the derivative on exponential is the exponential. And so a good guess for this, right? You have a derivative of 5 and 5. It could be the exponential, right? So you have this. But this quantity here could have different forms, right? So it depends on what Pn is. So one possible solution, one possible approach is to make an assumption. So of course, all this proof depends on this assumption. This assumption is not, it's pretty realistic assumption, and there are motivation, and I will tell you in a moment what are these motivations, but it's called a zip law. That is another power law. So you're saying, you're telling us that the price responds as a power law invoking another power law. Well, that is what is done many times in physics. When Newton was explaining why Kepler's law worked, he explained it through bringing in a new power law. There was the force of gravity, right? Kepler's found how the planets rotate, how long it takes for a planet to rotate around the sun, depending on their distance. And then Newton explained it more deeply by invoking another power law that was the force of gravity. So you're saying, well, but you're not explaining anything. We do, because we are going a little bit deeper. It is not completely clear why it should be some kind of square relationship in discovering the price, right? But I'm saying here, all what you need to invoke, that there are a bunch of actors in this network, and their activity level, it's organized in this way through this Z flow. And you will see, because I will show you in a moment, that people found empirically that is the case. It's kind of similar to what the Pareto law that Stephen was talking about. You see that it's something that almost everybody shares. Like if you ever have been in a club, right? Some kind of any type of social club, there's always a small group of people, they say 20%, that does 80% of the work, right? Everybody else is a slacker. They never show up to meetings, etc. Then there is an active core of people that do most of the work, right? And that shows up also in income distributions, etc. There are some people that are more active and less people, and some people that are not so much. And when you're looking at this distribution, it looks like 1 over the number of people that are involved. And this is what I'm invoking here. There is some kind of a constant. That constant, we will have to find it empirically, but the important thing here is that it's the activity level, the probability that this person is involved in this system goes with the number of people. Also because as you have more and more people, you will have more and more slackers, right? And so there are many people that don't do anything. They buy Bitcoin, maybe this is it. They don't do anything else. They don't buy more in the future. They don't participate to the transactions, etc. So 1 over n, this is what we are assuming. So if I substitute, right, or some constant over n, so I substitute this constant over n in my equation here in this differential equation, then I solve it. If you know a little bit of, so what you can do, you can take you integrate this thing, right, from on both sides. And if you know any calculus, this is what you get. You get that the solution for this right side is nothing else than some constant times the logarithm of n plus a constant. And this should be familiar for anybody that ever look at some of my mathematical demonstration of the power law, because basically you're taking the log of a y-axis, the log of a x-axis, and it looks like a straight line, right? Because you have a constant multiplied by x, where x is the logarithm of n. This you have a logarithm of y, and that, if you take the exponential of both sides, and so to eliminate the log, you get a power law. You get that phi n is nothing else than some constant times n to the gamma, where now this gamma is the exponent. And in our case, empirically, is close to 1.8. It is kind of less than the Metcalfe law, but it's a generalization, right? It turns out, and maybe I can cover, because we are going out beyond our time, maybe I can cover this next time. It is how this changes when you're dealing with more influential nodes that are more powerful. Can you modify and generalize even more? Because that is another result that I found. I did a study where I look at different wallet cutoff, right? Wallets that contain 1 Bitcoin, 5 Bitcoin, 10 Bitcoin. And I found Metcalfe laws, but with different exponents. And the exponents became bigger and bigger and bigger as you go to bigger and bigger wallets. And so can we generalize this to different wallet size? And so, and we can see that this argument holds, and we can reproduce the empirical result by, again, making a small assumption on how the wallet size influences this exponent. But we can cover that next time. It's a lot of math for today. But basically, what I was trying to show, that using some simple assumptions, we can explain why we see this kind of nonlinear behavior between adoption, so the number of users, because addresses are a proxy for adoption, and the price. And it's not the S curve that many people invoke. It's a power law, it's power law everywhere. And here, some of the argument why the zip flow that I invoke to assume how the level of engagement of every single actor, agent, right, is in this network, it shows up everywhere. Like, for example, content popularity in different social network follows a follows a Zipf's law. How different users use different type of online platforms we follow. So all things that have to do with social network, a lot of behavior is controlled by this Zipf law, resource allocation, engagement matrix, and so on. So it's not a completely crazy hypothesis that yes, these agents in the network will have different level of engagement that follows that Zipf law. And from the Zipf law, then we can derive Metcalfe law. So Metcalfe law, it's like basically this is like a Newton's law, and the Metcalfe law, it's like Kepler's law. It's a derivative from something more fundamental that has to do with how people or resources are distributed in a network. So it's I think it's a very interesting result. And this is a paper actually that describes it, because you can have another popular terminology for this distribution. It's the 80-20 rule, or maybe sometimes also the 99-1 rule or principle. In this case, it's a little bit more distributed. There is 90% that does a lot of work, when there is 90% 90% don't do almost anything, and there is a 9% that does a little bit more, and then there is 1% that are the most active, one that moves more things around, and so on. And this appears everywhere, right? You were telling me that actually we see this in astrophysics, in physics, right? The galaxies, etc. Stephen, you were mentioning that. What happened to Stephen? You're still there? We don't hear you.
Have to adjust input volume. The 90-9-1 applies directly to clusters of galaxies that are 90% dark matter, 1% ordinary matter in the galaxies, and 9% very hot, multi-million degree ionized plasma between the galaxies.
Yeah. So it's something that happens often in nature. Is a question of how nature organizes itself, and things interact with each other. So what do you think about this proof? It's a very simple proof, but I think right idea.
Well, I guess the only question is, should it adhere to Zipf's law? What's the reason? And I guess the reason is by analogy with many other systems, and it's certainly true for many economic and socio-economic systems.
Right, exactly. So it's it's sometimes, and it's funny, right? Where like how in physics many times we try to answer a question with another question, right? Or power law, another power law, because it's kind of a little funny. Right? Say, why there is a power law in Kepler's law? Well, because there is another power law, but it's a more fundamental power law because it's more universal. Tell us that there are all these objects in the universe are interacting with each other with this force of gravity, etc. And so it basically says, well, it's not a fundamental law; it's a derivative. It's a behavior that is based on this more fundamental law. And so this is what we are trying to say, that the price responds non-linearly as a power law to the number of agents in the system, because it's based on some more fundamental principle like the Zipf law that has to do with how resources get distributed in a system. So it's not the end of a story, because we could explore why that happens, or why Bitcoin is a network or whatever, but it's a step in that direction. Okay. Do we want to answer a question? There is like one question, but I don't know this. I think I read something about this, but I don't know if you are more.
I cannot. I don't know enough about the latest discussions going on there to comment.
Yeah. But did you hear something happening? There is some debate.
I've seen reference to it. I've checked a little bit, but I'm not following it closely enough to have a comment at this point.
Yeah, me too. I wanted to explore it myself more, because I know that there is some debate about these and some proposals about some code update, etc. But I also didn't follow enough to give a reasonable answer about this, so I don't know. Okay, I don't think we have any. Do you see any other interesting questions? No. Okay. All right. Then, if there are no questions or comments or anything, we can. Do you want to make some concluding remarks or some announcement or anything, Stephen?
No, I just want to thank everybody for joining tonight. Thank you.
Okay. All right. Thank you so much, guys, and we will see each other next week. So, bye, everybody.